In this video, we're going to talk about how to model data, and this is just going to be a very basic video, a very basic intro. And so this is really meant to give you a taste of how we go about creating equations, but there are many additional classes you can take that go much more into depth on what we're doing. So statistics class would go more into depth on this, and then more advanced statistics classes. You might take a regression modeling course or a regression analysis course, and that's going to go more into depth on this stuff as well. So the idea behind this, in math, we get very comfortable with the idea that, hey, we're given the equation and then we do some stuff with this equation. We never really see where it comes from and we don't understand why we're using it. And that's not what happens in life, right? A problem doesn't just walk up to us and hand us the equation. A bridge doesn't just hand us its equation. A weather system doesn't hand us an equation. We have to go and discover that equation. We have to figure out what that equation looks like. And that's what we're going to do in very basic terms in this video. So we're going to find the equation for a scenario. The way we do this is we'd have to first collect data, right? That's always the first step. You collect data. We're going to be given that data because we're not going to actually be going out collecting that data. I'm going to give you a table here. But scientists and mathematicians have to go out and collect that data. From there, they need to figure out what type of equation best models that data. We've seen many different types of equations: linear, exponential, higher degrees of polynomials. We've seen logarithmic. We've seen many different shapes that data can come in. There's sines and cosines down the road. Once we figure out what model works best, we want to actually find that equation, and then we can use it for our own calculations, for our own purposes. The equation that we're going to create is called a regression equation, and it is seeking to connect all the data points in the best way possible. So we know that curves are smooth. They aren't these jaggedy things. We can't just connect three data points that don't line up exactly. We have to connect them on as smooth of a path as possible. And so that just means we won't hit every point exactly. And that's why we're dealing with a regression equation, is seeking to best fit all the data at once. So we're going to be working with an equation, with an example here. And in this example, I've given you the year in American history and the life expectancy. Now, I've kind of made up some numbers based on approximation, so I don't have concrete data source for this, but this will give us a good idea of how to do the model. So we have the year versus the life expectancy. And so we're going to be using our calculator a lot in this video to help us come up with these equations. Like I said, in a stats class, you would learn how these equations actually work and where the numbers come from. We're just going to rely on the calculators to give it to us. And really, once you understand how the stuff works, that's all statisticians doing too. They're just doing using technology to come up with these equations, but we do want to understand where they come from and what's going on. Now, the first thing to always realize is that when we're dealing with data, there has to be an input and an output, what we call an X and a Y. Now, the first row we might think of as the X, and that's not always a guarantee. We always want to think about the data and try and make sure that we kind of have it right versus the independent variable versus the dependent variable. I think that the year would be the independent variable, and that's true because the year is going to happen no matter what, right? Time's going to move on no matter what. That keeps happening. The life expectancy is based on that year. Now, there is something really important that I want to say, which is a correlation, meaning that two things look like they are related. Correlation does not imply causation. And so what is this idea of a correlation? Correlation means that we're going to see that two variables are related. So for instance, if I were to plot this data, which we're going to do in just a few minutes, let's say I had 39 and then I plotted its y value and it's 810. The x value of 810, plot its y value of 39. Then I go over to 910 and its y value is 51. And then I see the next point, and then I see the next point. These are all looking like they're lining up. There seems to be some trend to this data. Versus if we saw something that looked like, that doesn't appear to have any trend. There's nothing really going on there. So there'd be no correlation here. Versus if we saw this sort of picture, it definitely seems like as the year progresses, life expectancy is going up. That's not necessarily what's happening. We don't know yet. So this would imply a correlation, meaning these two variables are definitely related. As one increases, so does the other. Or if one decreases, so does the other. Doesn't mean that one causes the other. Now it might, right? There are situations that we know that there's a cause and effect. If you eat lots of unhealthy food, if you're eating chips and cookies and cakes every day and just, you're eating tons and tons of food and you don't eat a lot of fruits and vegetables, you're going to have worse health. You're probably not going to live as long. You might have diabetes. You might be overweight. So there are things that we know through science, through studying it long enough, that one thing causes another. However, that's not true in every situation. There are plenty of things that two things might be related, yet they don't actually cause one another. So for instance, there is a strong correlation, there's a strong relationship between temperature and, sorry, let me back up. There's a strong correlation between the number of ice cream cones sold and the number of drownings. And I kind of gave away the relationship here. So we could put ice cream sales here and drownings here. That's not to say that ice cream causes drowning. They are correlated, meaning if ice cream sales go up, so do drownings. However, like I said, I gave away what the answer is. The causation is probably more through temperature. If it is warmer outside, more ice creams are being sold down on the boardwalk, and there are also more people out swimming at the beaches, and so drownings are also going to increase. It doesn't mean that one is causing the other. So there can be what we call lurking variables, or just a third variable sitting there causing both events to happen. It could be that sometimes we assume a causation and we get it backwards. So let's say I was an alien coming to the Earth and I didn't understand anything going on. And I am standing out in this field and I see lots of wind and I feel this wind blowing on my face, and I look up and I see this big wind turbine, a big windmill. I might say that, hey, that windmill is causing the wind because I didn't know any better. But I've clearly gotten that relationship backwards, right? So we've got to be really careful that when we're seeing that two variables are correlated, we don't imply causation. And the other idea behind that is we might sometimes have these in the wrong order. Like I said, time pretty consistently is our independent variable, but sometimes it's not as clear. Sometimes we're not sure which thing is really the independent versus the dependent. So in this video, the reason I'm stressing all of this, we're never going to assume causation. We're never going to say that this causes this to happen. But we can see that two things are definitely related, right? Okay, at this point, what I'm going to do is I'm going to go ahead and pull out my calculator. So if you would pull out your calculators, we're going to enter this data and we're going to see what it looks like. Right, so now I have my calculator up, and the first thing that we need to do is put in that data set. So the way I'm going to do that is I'm going to have to go to, first turn the calculator on, and then I'm going to go to Stat and Edit. And so to save time, I've gone ahead and put the data points in here, and this will make it easier for you to copy them into your own calculator. So I'll give you just a second to do that. But you'll literally just type into that blank list. So your list is currently blank, hopefully. You type in, say, a 1, then a 2, and you go the whole way up. If you do have things in those cells, you can get rid of them by hitting the delete button, and it'll just get rid of that cell entirely. But we want to type in the years 1890, 1910, 1940, 1950, 1970, 1990, 2005 to 2015. And then in the Y's, we want to make sure that we match them up correctly. We didn't miss anything. Next to the 1980, we should have 39. Next to the 1910, we should have 51. Then 62 next to 1940, 67 next to 1950, 70 to the right of 1970, 75 to the right of 1990, 77 to the right of 2005, and 78 to the right of 2015. And so then once we have all of our data points in there, what we want to do first is we want to look at what pattern this makes, because remember, the first step in deciding the model to use is we want to see what that picture looks like. We want to get a feel for what we kind of are dealing with here. So the way I'm going to do this, first thing I'm going to do is I'm going to hit the Y equals button. Now all my plots are empty, but you may have graphs in your calculator, so if you would just clear anything from this screen. The next thing I'm going to do is I'm going to go to second, Y is equal to, and so notice these are my stat plots. We just entered data into the statistics list, or the stat list. So I have to turn this plot on so it'll show me these points in what we call a scatter plot. And so to do that, I'm going to go to this first point, I'm going to hit enter, and I'm going to toggle it to on. So when that cursor is blinking on, I'm going to hit enter, and notice it's turned it to on. Now everything else you can really leave, everything's fine by default. The little dots are the most helpful, and these little square markings are the easiest to see. These are very hard to see. The pluses are fine. I like all the defaults here. The only thing you might want to change is if you're entering multiple lists into your calculator. Remember, if you go back to that editor, it has multiple lists in here. I entered mine in L1, L2. We want to make sure that we are choosing the correct list. And so we have done that L1 and then L2, and then we talked about the fact that L1, the X variable or the independent variable, we don't really know for certain, but we always assume that year to be the independent variable when we're entering data or a time. Okay. So now that we have that set up, if we were to get a graph, let me go back to your standard zoom. I most likely won't see anything, and that's because I'm not zoomed to the correct area. So I'm going to put it back to how it was just a second ago. I'm going to go to zoom, and then I'm going to go to zoom stat, which is zoom 9. You could zoom out until you saw the dots, but it wouldn't necessarily zoom in the best window screen, so it might be a little bit hard to see. So when I go to zoom stat, all the dots display nicely. So if we think about the type of functions that we've dealt with, we've seen exponential, most recent, one of the more recent functions, exponential functions. Well, these don't seem to be shooting off to infinity. If anything, they seem to be slowing down. They're close to a line, but it definitely seems like there's a little bit of a pattern there to where it's kind of arcing a little bit. It's definitely not quadratic. It's definitely not creating that U shape. It's, you know, the closest thing I think we're seeing here is a logarithmic pattern. They do appear to be bending in that logarithmic shape. So that's leading me to believe that a logarithmic model will be best. That is what I'm assuming. However, math doesn't work off of assumptions and just appearance. So there are some more formal ways we can show that this model might be the best, and we're gonna see that. Okay, we're gonna see that in just a few minutes. So, good idea to look at the scatter plot. This is called a scatter plot. We've plotted an x-coordinate compared to a y-coordinate. So each of these points is just the the point 19, 10, 51. It's plotted right there, and then we have the point 19, 50, 67. It's plotted right there. So then the next thing we're going to do is we're going to try to create a model that will essentially connect all these dots in the best way possible. And that model is called the regression model or the regression equation. Sometimes you might hear it called the line of best fit. That is true for linear regressions because it is a line. We're not dealing with a line here, so we have to use that regression equation terminology. And so the idea behind that regression equation is it's going to put a curve into this model, and it's going to do so to try and get as close as possible to all of these points. So for instance, if I were to put a curve here, I might miss this dot right here. It's not really lining up with those other two very well. But if I were to move it down to hit these two dots, then I would miss these other two. So we're trying to put a curve in here that best matches all of them, but it's not going to be dead on every point. Because life never works on a straight line. Life never works on that perfect curve. So there's always going to be some natural variation. We see that every point doesn't quite line up. So let's see how to do that. I'm going to hit second mode just to get back to my calculation screen. Then I'm going to go back to that stat button. Well, actually, let me back up for a second. First thing we need to do is we need to turn on the diagnostics, and that's going to show us what's called an R value. And once you turn this on, as long as you don't reset your calculator or change the batteries, this R value will stay in there, but we need to do that first. So I'm going to go to second, and then to the 0 button, which looks at the catalog. I'm going to scroll all the way down until I see diagnostic on. And I said it turns on the R value. You have no idea what that means yet. That's fine. We're going to talk about it, but we just need to turn it on for right now. And we're going to leave this on. The calculator, like I said, will default to leaving it on as long as we don't reset it. So we went to the catalog, diagnostic on, I hit enter, I hit it again, and notice it says done. All right, so now I'm going to go to stat. And rather than editing the list this time, I want it to calculate something. So I'm going to go over to calculate. We see all sorts of things, and a lot of these things, like I had said before, this is a lot of what statistics does. A lot of what you would do in a statistics class are these sorts of regression models and regression analysis. So we see some just variable stats. It'll give us means, medians, standard deviations, things like that. We don't need to worry about these. We have the lin-reg, linear regression, or creating the line out of that data. We said the line's probably not the best, but let's just see what else we have available to us. Quadratic regression, a cubic regression. The quartile regression we're not going to worry about. We haven't really talked about those a whole lot. The linear regression, this looks kind of the same. The only difference is it's reverse position of the slope and the y-intercept. So it's not saying the a values are the same. and the b values are the same. It's just if we found a to be 5 here, the b would be 5 here, and if b was 2 here, then the a would be 2 here. It's just switching the position of those, and there are reasons for that. We're not going to get into that. I don't care enough. It doesn't matter which one we use because we know we can always switch those a's and b's. Then we see a ln reg, which does not stand for ln reg. It stands for the logarithmic regression, because remember the ln is the exponential it's the natural logarithm. So we have the natural logarithm, and then we have our exponential regression. We have a power regression, a logistic regression. We're not going to deal with any of these other ones here. We're going to primarily concentrate on the linear regression, the logarithmic regression, and the exponential regression. Now I'm going to start with the linear regression because we said it didn't look like a great fit. So let's go ahead and find that linear regression. L1, L2, good. That's the same thing we had set just a second ago. I'm going to go down to calculate. And so here is my information. Notice it gives me the shape of the equation first, y equals ax plus b, what we're used to line looking like. A is equal to 0.2987, excuse me. It goes on forever and ever. It's not a nice pretty number, but we can round it to, we'll say round to 2 decimal places for today, so 0.3 x plus a negative 520.29 for our y-intercept. So we have the model that would give that to us. Notice we have an r value and an r squared value. For right now, I just want to write these down. So I'm going to write down my r value of 0.96969. And we'll talk about this more in just a second. So when I switch over to my other screen, we'll talk more about this. So there would be our linear regression. Let's do the same thing this time for the exponential. So let's go over to calculate. I go down to exponential. And I should note too that if you're using a TI-83 calculator, if you were to hit enter at this point, it's not going to bring up this screen. Okay, so I'll just move on to what it'll look like in just a second. But for the 84s, it brings up the screen. We want to write L1, L2. We'll go down to calculate. And so once I do this, 83s, for just a second, you're going to see what your screen looks like. It has that EXP reg at the very top. I'll do that again. Unfortunately, I can't make the calculator stop midstream, but it's going to pull up that exponential reg, and that's what yours looks like. It's going to say that at the top of the screen, and then you have to physically type in the L1, L2, and the way you do that is by hitting second L1 and then comma, second L2. So you do the same thing I just did. You bring up the stat, calculate, type in that EXP reg, hit enter, but then it puts it up there at the top of the screen. Then you physically have to type L1, second 1, comma, second 2. All right, so our exponential regression has an R value of 0.9436. And then, like I said, the last one I want to look at for today is the logarithmic. So I'm going to go over to the second calculate, ln reg. And again, 83s, if you're to hit enter right now, it puts in the calculation screen. It does not bring up this screen. And then you'd have to type in the L1, L2. And so I see my R value there is 0.9718. I'm going to go and write down the R squared on this one too. We'll talk about that more in just a second because I haven't really mentioned the R squared much at all. All right, so now I have some data. I have the physical equation. So again, on the natural log here, I would know that the equation would be equal to negative 4,367.67. And then our b, we'd have the plus 584.78. And that's attached to the natural log of x. So let me go ahead and switch back over to my writing screen, and we'll talk about these numbers a little bit more. So we said that there is a number that tells us really if a model is best. I said just by looking at the picture isn't quite good enough. And then we talked about this R, we found this R, yet I didn't talk about it at all. And so I've written a bunch of stuff on the screen, and now we're going to talk about that R. What's going on? So let's do our over here on the right hand side, and that is R. The R is called the correlation coefficient. And that R value is always between -1 and 1 inclusive on both ends. It can't be less than -1, it can't be greater than 1. It's never going to be 1.1, it's never going to be 5. A 1 indicates a perfect correlation, meaning those two variables could not be any more related. There's nothing else involved, one perfectly ties into the other. That rarely happens in life. We talked about on the picture, those dots don't line up perfectly, and they rarely will in life. That basically never happens. There's always natural variation. There's natural things that are occurring. And so if we think about our example, year versus life expectancy, uh, we can see that with time it's definitely going up. We saw that in the picture too. It's slowing down, right? We're not just going to keep jumping 20 years every, 50 years. But, we might hit 90 one day and it'll continue to increase. But there are things that naturally make that go up and go down. Not every year falls in line perfectly. So, for example, in the early 1900s, we had World War One. That really reduced life expectancy because people were dying at a younger age. In the 40s to the 50s, we had World War II, and that again was causing a different result than we would have otherwise expected. We have other events. We might have worldwide pandemics. We might have some sort of food shortage or some sort of natural disaster that really drops the life expectancy or the average age of a given year. Wars tend to be the biggest influencer because they go on for prolonged periods of time, and they really have a large casualty associated with them. So we don't expect the perfect ones. And so we have to kind of make a judgment call. And that's oversimplifying this by a lot. This table is oversimplifying the situation by a lot. Here I've said that if our R value is greater than 0.9, that is a very strong correlation. Notice I've put that in absolute value. Because a 1 is a perfect correlation, so is a negative 1. It's just a negative 1 is indicating that things are trending downwards. As time goes on, the infant mortality rate would be going down. So that would have a negative R value because as one thing goes up, the other thing goes down. Versus our situation, as the years go up, the life expectancy also goes up. So here, I don't care which side of the plus or minus it's on, I just care about the value or the absolute value of the number. So anything greater than that 0.9, very strong, we can nearly definitely assume that there is a correlation there. Between 0.7 and 0.9, those are still strong correlations, and that's a lot of times where we see things fall. They aren't always greater than the 0.9. So usually a meaningful correlation. Between 0.4 and 0.7, those tend to be moderate, and so then this becomes really kind of the question area. Is there something actually tying these two things together? Is there a relationship between them? And sometimes the answer is yes, and sometimes the answer is no. Less than 0.4, this tends to be a weaker correlation. Again, doesn't necessarily imply that there is no correlation, and there is a formal test to test whether something has a meaningful correlation, whether there is actually a relationship between things, or whether it's just kind of happen chance that a correlation is showing up. And just like we never get the perfect ones, we never get a perfect zero. It just never happens. Things naturally happen to line up, right? If I was to look at the number of Cheerios I ate in my breakfast this morning versus the number of hours I slept at night, those two things are absolutely not related in any which way. But if I were to graph them, I'm sure that there would be a R value of something like 0.1, 0.2. Just you never see a perfect zero. And so there is a formal test to see really where do we fall in the meaningful spectrum. And like I said, something that can look quite strong, like 0.8, might actually come up as not meaningful because other variables are really playing into it, or it just kind of was lucky chance. Versus sometimes we might see an R value of something like 0.3, and that might actually have a meaningful relationship. It might be that that one variable is contributing in some way to the bigger picture. There could be oftentimes multiple variables, like we've already talked about. Year's not the only thing influencing this life expectancy. Eating habits, whether there are natural disasters, wars. So if we incorporated all those things, our R value hopefully would get better. And there are ways to incorporate multiple variables into a given scenario too. We're not going to do that here. So I've written down my R values that we found just a minute ago. The linear was 0.9696, the exponential 0.94, and the logarithmic was 0.97. Now, all of these appear to be meaningful because I think if we were to go back and think about those dots, we saw the pattern that looked kind of like this. They weren't on a perfect straight line. That's over-exaggerating a little bit. But could we have fit an exponential curve through it if we reflect it, turned it upside down? Yes, we could have, right? We could somehow get an exponential curve in there. Is that the best model? Probably not. And then we had our linear. We said at the time that definitely looked like we could fit a line to that data. Get rid of this curve. And so if I were to try and put a line through this data, again, does it kind of fit? Are the dots close? Yeah, absolutely. It definitely looks like there could be a linear trend to it. Is it the best? We said probably not. We said, you know what, the best looks like it should be that logarithmic because it looks like it's kind of leveling off with time, but not necessarily reaching an asymptote. Can't tell, not enough time, not enough data. Uh, and so that's what the R value is telling me too. If we look at this R value right here, that 0.97, that is higher than any of the other models. We said linear, the exponential wasn't really in contention here when we looked at the picture. Notice its R value is the worst. The linear is close. It's only off by a couple thousandths, but it's still not as good as that logarithmic. And so sometimes these will be more distinctive even. Sometimes we might have an exponential of 0.7 and the linear might be 0.8. But usually there's going to be some correlation found through all three models. They're all going to look decent if there is actually a correlation. We want to find the one that has that best R value. That is our physical proof that we have the best model possible to us. And so from here on out, I just want to talk about that logarithmic model. The R value is telling me that we do have what appears to be a very strong correlation, and the logarithmic model is best. And so I've just copied my screen down so I don't have to jump back and forth. But let's write out that equation again since we know a logarithmic model is the best. Y equals negative 4,367.67 R B 584.78, and then we have our natural log of x attached to that. And so now we can use this model for anything we wanted. So if I were to ask, what was the life expectancy in the year 2003? Well, that's not actually in the physical data set, but we could take that 2003 and we could plug it in. Or if I were to ask, what is the year in which the life expectancy was 74? Well, this time the 74, because that's the life expectancy, I'd have to plug it in for my y, and I'd have to solve that equation. So we're using all those skills that we've been learning, how to solve exponential, how to solve linear or logarithmic equations. It's just we are actually creating that model at the start. Now, what if I were to ask, in what year is the life expectancy going to be 120? We could plug that y value in. We could find that. But the thing there is, are people ever going to live to 120? There's a lot of evidence, a lot of science saying that there is a max age that we'll kind of reach, and just it's impossible to sustain that human life expectancy forever and ever. And that's what we saw by the model leveling off. And so it might take billions of years to get there, but it might just be that we never get there either. So we have to be really careful of something called extrapolation. And extrapolation is when we take the data set too far, trying to predict outside the data range. And so, do scientists do this? Absolutely. That's the whole point of weather. We're trying to predict what hasn't happened yet. It always comes with that kind of side note. This is a forecast. It is a prediction. And usually there's a given amount of error associated with that. You see that in polls too, that we think Canada today is winning by 20%, but there's plus minus 5% that we're not sure of. Any good poll or any good statistics should have that with it. So if we're trying to predict something like when the age will reach 120, that's just way too far out the model to try and predict. That's like me saying, let me predict the weather in the year 2059 on Sunday, the third Sunday in March. Well, I just can't get an accurate model for that. I don't know what it's gonna look like. Can I predict some maybe larger trends? Maybe I can start to try, but it still comes with a very big asterisk. Likewise, I can't go too far the other way. I couldn't say, what was the life expectancy in the year 0, right? I could plug 0 into my equation. Well, I can't even plug 0 in because I know that's an asymptote. But I could plug 1 in, I get 0 there, and I'd get, so in the year 1, we'd predict a life expectancy of negative 4,367 years. Obviously, that's not true, right? That's too far outside of our data range. So at some point down here, the model just kind of broke. And so is it okay to predict a little bit outside the data range? Can I go up to maybe 2020? Maybe. Well, we're in that year, so we'll have pretty good evidence here shortly whether we were right or not. We'll see if this model really holds. Could I go down to, say, 1880? Again, probably that's fine, but I just need to kind of put an asterisk when I'm doing that work that, hey, I'm extrapolating here. We want to be really careful of, though, when we're trying to predict way outside that data range. If you said to me, find the life expectancy in the year 2000, 999. I could plug into this equation, but I wouldn't even do it. I just say, that's extrapolation. That's trying to predict too far outside of the data range. Or if you said, when was life expectancy 0? I'd say, that's just not a realistic question. That's extrapolation. It's too far outside of my data range. So we always want to be careful that we're not predicting things well outside the data range. That is, again, called that extrapolation. Sometimes you'll find that if you were to plug in an actual year, so for instance, if we were to plug in 1990, most likely it would not be the same number. So I'll let you do that on your own. Plug in 1990, see what you get. And I'm betting it won't be 75. And that's not a bad thing because remember, we had all these dots that were kind of all over the place and they didn't fit directly on that model. We're trying to fit that line as close to all of them as we can. It's not that we're going to pass through every one exactly. And actually, this is kind of crazy thing. Sometimes the model actually makes a more accurate forecast or a more accurate result than what actually the data tells us happened in that year. Think about how hard it is to collect data, right? That's like we're doing the census this year, 2020. The census, think about how hard it is to collect data from every single person. We send mail to people's houses, we call them, we knock on their doors. But what if that mail gets lost on its way to the house? What if you work during the day and you're only in at midnight, right? Or if you work that early shift and you only come in the very late evenings of the evening, well, chances are that census worker is not knocking on your house at 1 a.m. Same thing with the phone calls. You might miss it. You might not have a phone at your house. You might not have a house. And so how do we count you then? And so it's real hard to get accurate data. That is a big challenge of statistics. And that's something that statistics also tries to account for. It's saying, hey, anytime we have this data, this might not be perfect. And so sometimes actually what we can do is we can build a model and it's more accurate because it takes out some of that little variance. Like, oh, Johnny wasn't home today. He is at work. Or one of the big problems is we always have a double count of students. Student goes off to college. They think, oh, I'm my own person. I'm going to fill out my own census. Mommy back at home says, oh no, little Johnny is still my little boy. I'm going to fill out the census for him. And so now we have this person counted twice. And statistics looks at all that and they take it out. So again, we can build the model sometimes more accurate than the actual data. And so, we expect to get different results. We can predict years that we don't have data for. We can predict years that we do have data for. And it's not always going to be dead on. The pattern that the model gives us is this smooth curve versus our dots jump around a lot more. Little bonus too, I forgot to mention the R squared. R squared is called the coefficient of determination. You don't need to know this for this class. In a stats class you would. So that R squared gives us the percentage change in the Y that can be accounted for by the percentage change in X. Again, if we could assume that causation, it'd be how much of the Y is changing because of the X. If we don't have a causation, we can just say, well, in this case, 94% of the change in life expectancy is predicted based on the year. And so that would be what the R squared is. So hopefully this has been a good intro to statistics and to regression models. Many additional classes you can take on this, but for our purposes, we want to be able to come up with that model so that way we can use it the same way we've been using the equations that have been given to us. Just now, we don't have to be given that equation. We can take data and we can create the model off of that.